Yes, and we are live again, and it's a pleasure for me to introduce the speaker once again to you. Ma'am, with your permission.
Please go ahead.
So, Dr. Sourav Sur has been working in the Department of Physics and Astrophysics, University of Delhi. He has done his PhD in 2005 on the thesis entitled Cosmic Phenomena in String-Inspired Space-Times with Torsion from Jadavpur University, Kolkata. He had worked as a postdoctoral research associate at Institute of Physics, Bhubaneswar, India, University of Lethbridge, Alberta, Canada, and Saha Institute of Nuclear Physics, Kolkata, before joining as a regular faculty member at the Delhi University. He has taught many core and special theory and lab courses in the curriculum of the master's degree program at the Department of Physics, University of Delhi, and his main research areas include classical and quantum gravity, cosmology, quantum entanglement, and black holes, astrophysical and cosmological aspects of a string. He has more than 25 research papers and has guided many PhD students so far. His name is included in the reviewer panel of several research journals of international repute and have received recently the Outstanding Reviewer Award of 2019 from the Journal of Classical and Quantum Gravity, Institute of Physics Publishing, Bristol, UK. Saurav, we all have to learn cosmology. Please ask me why. Because cosmology and string theory um, is the fashionable physics these days, either gravitational waves or cosmology or astrophysics. When I ask a student, why have you taken up physics? And the prompt answer comes in, I want to study cosmology. And I think, oh God, I better brush up my cosmology details of research now. So you're working in fashionable physics is what I call you, because everybody wants to study cosmology and astrophysics these days, apart from
Yeah,
material science. Apart from material science, that's it. So welcome again, and please share your slide and deliver your lecture. Thank you.
Yeah,
okay. Thanks.
welcome, Dr. Sir.
Yeah. Can you see my screen?
Yeah.
Okay. So let me get back to where we were. Just one correction. These are the first set of notes. Those who have missed the first set of two lectures, for them, I guess I'll share the link for a bit of older version of the full set of notes, as I'll do it shortly. Just one correction to the notes already supplied to you. I have missed out. That's my apology. I have missed out one very important reference. Okay, based on which these notes are based. That is a book which is being used is to be used for all many sorts of core papers, especially at the master's level. And you all know that there is a series of books by Landau and Lifshitz. Okay, so, uh, among which there is one book on electrodynamics, that is the I forgot the volume. It's volume 5 or something. That is the electrodynamics of continuous media. Okay, I'm not referring to that book. Remember, there is one book which is very common in that Landau and Lifshitz series. That is the volume 2, Classical Theory of Fields. Okay, so yeah, so I have added this reference. You can see the reference 2 here. Okay, so this is one of the main textbooks. I'll mainly be following Jackson, Landau, Lifshitz, and for the relativity part, Weinberg. Okay, also for the relativity part, Landau and Lifshitz. Although Landau and Lifshitz have some weird type of notations, which I'll not make any allusion. Okay. I'll mainly follow the notations of Weinberg and Jackson. Of course, I guess the notes are self-sufficient. The notations are explained. I'll use the Gaussian or the CGS system of units. If anyone wishes to go to the SI unit system can do the appropriate conversion. Okay, so the first set of lecture notes were on a brief review of Maxwell's theory of classical electromagnetism, and after that, I went to explain what was the problem with uh, Maxwell's electromagnetism with then existing Galilean relativity or Newtonian relativity, and what was the need to formulate a new principle of relativity and to find a new set of transformation equations, which would replace the well-known Galilean transformations then existed. Okay. Coming back to the worksheet, let's do some problems. I guess many of you have tried these problems at home and possibly, probably tried successfully. But still, for the general audience, I'll work out on hand certain problems of this set, which will give you some flavor of how to deal with things with these kinds of problems. Okay. Before going to that, let me tell you one thing, that these worksheets are just illustrative problems at the beginning. The main problems would come later. Specifically, the last 3 to 4 lectures in this series would be completely devoted to problem solving of specific categories like the electromagnetic field transformations and the motion of charged particles in electromagnetic fields. All right. So this is the first problem. It is the well-known Ampere's law or Ampere's circuital law. The magnetostatic force between two small current loops C and C prime with tangential length elements TL and DL prime, just as you see here. Okay, I think I have missed this. The length elements are DL and DL prime. Uh, uh, and carrying currents I and I prime respectively is given in Gaussian units by this formula. This is the expression for the magnetostatic force. Look at this. This is quite similar to the Coulomb force in electrostatics. What is the Coulomb force? You have the two charges, and the mutual interaction between the two charges is given by the Coulomb force, which is, let's say one charge is Q, another charge is Q prime. Then the expression is Q times Q prime over C squared times R over R cube. Here, the charges are replaced by current loops. Current loops are given by the current times the line integral over TL. That is the tangential length element of the loop. So the Q in Coulomb's law should be replaced by I times dl, integral of dl. Okay. And the products, ordinary products there, are replaced by vector products. It's all the same. It's just analogous to the Coulomb's law. Only thing is that the charges are replaced by current times the integral over the tangential line elements, and the products are replaced by vector products. Okay. This R is the distance separation between the 2 points. One is located with respect to some origin O. The location of one loop is x prime, another loop is x. So R is the distance separation. So let's solve this problem. What you require to show you have to reduce this expression to this form. Okay, so that is the task you have. It's a very simple problem. It's a two-line problem. Okay. The next problem is also on magnetostatics. It has two parts, but I can tell you this is a very involved and long hand exercise. Okay, specifically the second part. So let's do the first problem here. So let's do it. I urge you to keep the worksheet open in front of you. This is the worksheet. You keep it open in front of you. And you have to reduce this expression to this form. Okay. As I was saying, the full set of lecture notes will be available. You can see this in my ResearchGate account. You can just put this, copy and paste this link in your browser, and you'll get the notes. This is an older version, though, not the one which is supplied to you, or excerpt of that supplied to you. But this is older version, which will cover most of the things. Okay, let me open for you the older version. This is the 2017 version. So you can see it's the same thing almost. The full set of notes containing as many as 11 chapters and 2 appendices. And we have completed the first 2 chapters. We'll do the third chapter, which is the formulation of special relativity, which I'll do today after this exercises, possibly in the next lecture today. I have 2 lectures. For the time constraint, I'll skip this part because this course is not devoted to relativity. It's rather, relativity is used as a tool for doing electrodynamics. So I'll skip this chapter 4. Chapter 5 is another tool which you require to know, but I'll do this quite quickly. These are very abstract things, but okay, I'll do as much elaborately as possible in the given time. Okay. Then the special relativistic particle dynamics. Once again, I'll do it quickly and skipping a few things. Then I'll go straight to the covariant formulation of electrodynamic equations and the transformation laws and scalar invariants. If time permits, I'll also try and cover this chapter 9. But I think time will not be there. So after chapter 8, we'll do specific exercises for the last 3 lectures. Okay? There are a plethora of exercises. So we have to cover as many as 7 topics, 7 sections here. The 4th section is skipped, and all other sections from 1 to 8 we cover in these lectures. Okay. So I'll endeavor to do that by tomorrow itself. That is by the 6th lecture, to cover all these 8 sections. And then tomorrow and day after tomorrow, I'll try and go into the problem sections, which are not in these notes. Okay, so for that, I don't have any compiled note, but I have handwritten notes which I can supply. Okay. But mostly, I'll try and do the exercises right here on the whiteboard. So let's do the first problem. Now, let's do it here. So the first thing you have to do, you have to use the vector identity. I guess there are many vector identities which are already supplied at the end of this worksheet. At the end of this worksheet, you can see there are many vector identities. Okay, I'll use one vector identity, which is the identity 13 here. Okay. So you can see a vector divided by the cube of its magnitude can be written as the gradient of 1 over the magnitude. So using that, using that, so what I'll use is that 1 over r is minus r over r cubed. So putting it here, I have I can write it like this. Now, the next thing is that this is of the form A cross B cross C. So you can apply the back cap rule right here. So you can write this as this is the back cap rule of vector analysis. But you have to be careful that there are integrals involved here. So this is your A, this is your B, and this is your C. So I can simply write this as two integrals. One is minus okay, because A and B, A means this integral, B means this integral. This is the integral over the curve C, this is the integral over the curve C, right? So you have to be careful because A and B are integral relationships. So you cannot use this, you have to use this. Okay? Because C is a function over which the integrals are to be performed. So C has to come at the end. You have this dot product, of course, and then the C. So you can write it like this. Okay. Now you have two integrals in place. The first one has the inner integral, which is dl dotted with the gradient of 1 over r. So let's do this. This is dl dotted with the gradient of 1 over r. You can use the Stokes theorem to, this is over the curve C. So use the Stokes theorem to convert it to a surface integral with the surface having the outward pointing normal S, n, and then the curl of whatever is left. curl of this stuff. But curl of gradient of anything is 0. So this is 0. So the first integral goes, and we are left with the second integral, which already has a minus sign. So ultimately, what I get is this. And using the first expression once again, this one, I can write it as and which is your requisite answer. Okay. So this is the first problem done. Now the second problem, this is quite straightforward. The second problem is a bit involved. So let's go to the second problem. The second problem is that the density J of a stationary current distribution localized within a volume V prime is generally conserved. That is, the divergence of J is 0. This is the conservation relation. The corresponding magnetostatic field evaluated at x is given by Bx is 1 over c times this integral. Okay. So what you require to do, you have to work out the following. Part A, the magnetostatic vector potential A in terms of J after you verify that B is curl of A. And second, you have to work out the curl of B in terms of J. Okay. So that's what you require to do. So let's do this. Let's add a page here. A couple of pages. Still live with some part here, so no problem. This is so we have dx equal to 1 over c integral over some volume, some source volume. Remember, it's given in the question that the current J is localized within a volume V prime. And once again, R over R cube is minus the gradient of 1 over R. So I can write it as 1 over C integral over the volume, over the source volume, then J cross gradient 1 over R. Now use one of the supplied vector identities. One vector identity is this. This is the curl of some scalar times some vector A. This whole thing is the scalar alpha curl of A plus gradient of alpha cross A. Now you see that you can write this as 1 over C d prime x prime, then gradient of 1 over R cross J x prime. Just this is a vector product, so I have interchange. I flip the minus sign. Right now, compare with this. This is gradient of. You can call this as alpha. See, compare with this. This is your alpha, and this is your vector A. So, therefore, you can write Bx as 1 over C x prime. It would be this thing would be the difference of these two, this one and this one. So this is curl of your alpha is 1 over R, and A, this vector A is J. So J x prime over R minus gradient of sorry, minus 1 over A curl of J x prime. Okay, because your alpha is 1 by R and A is J. So we're simply using this relationship. Now the second term in the integral is 0. This is 0. Why? Because this is a function of x prime, and this curl is a space derivative. Curl means its derivative with respect to x. Okay, x is the field point, the point at which the field is calculated. X prime is the level of the source. So it signifies the source dimension, and the integral is over the source volume. So you can see here the derivative is with respect to x, and your argument is this is a function of only x prime. So that means it is independent of x, and hence c. So this term goes, and similarly, since j is independent of x, it is only a function of x prime. You can write it as jx prime curl of 1 over R. You can write it this way. You can take out the j from this curl because this acts like a constant. So, and also you can see that this whole thing is a function of x only, whereas this integral is over x prime. So what you get is this, but remember that this R contains both x and x prime. So you cannot take this whole thing out of this integral. You cannot do that. Okay. Remember that R is x minus x prime, which I'm calling R. So since R contains both x and x prime, you cannot take this out of the integral. What you can do is that there are two operators. One is this integral operator, and another one is this differential operator. You can interchange them. So you can write this as curl of 1 over c integral okay. So you can write this as curl of A, some vector potential where this vector potential is the term inside the bracket. So this is the vector potential. This is a function of x because when you do the integration over x prime, you put the limits, and this R contains both x and x prime. So ultimately, what will remain is a function of x. So this is your first part of the problem. So we have worked out the magnetostatic vector potential in terms of J. Now the next thing is to find the curl of B in terms of J. Of course, the relationship is well known. It's you know that 4 pi J over C, but you have to prove that. And the proof is a very long exercise. Okay. So let's do the part B of question 2. Okay. So here we have curl of B x. You have to be very careful with the arguments. Now, Bx is already given. So this is 1 over C curl of integral 3x prime jx prime over R, just as we have found out. So this is your Bx. And I'm taking the curl of this whole thing. Now, curl of some quantity, some vector A is gradient of divergence of A. This identity is also supplied minus the Laplacian of A. So apply this. Here you have 1 over C. Then you have what you can do first up is that you can change the integral. Write this as 3x prime curl of gx prime over R. So that means we are interchanging this integral with the differentials. using the above identity. Now I have two integrals here. So the first term, once again, I have a gradient operator and I have an integral operator. I can change this 1 over c, gradient of integral okay, minus 1 over c integral, sorry, Laplace of integral x prime. Okay, so I have this. Now let's work out this thing. Let's work out this integral first. So what I require to do is to work out 3x prime divergence of jx prime by r. Now once again, this is the divergence of a scalar times a vector. So I can write this as 3x prime just so d3x prime, I can write this as scalar divergence of jx prime plus jx prime dot gradient of 1 over. This I'm using divergence of alpha A is alpha divergence of A plus A dot grad of. Here alpha is 1 by r and A is J as before. So this thing, now this is 0. Why? Because, not because of the conservation relation, just because this is a derivative with respect to x and this is a function of x prime. So this thing is 0. This will go. Right? This is 0. And hence, I have 3x prime jx prime dot 1 by r. Now, what to do with this? This is the big question. What to do with this stuff? Uh, we have to evaluate this. Now, this is a derivative with respect to x. What is r? So you have gradient of 1 over r. That is gradient of 1 over x minus x prime. So this is simply, if you take the what is the relationship uh, of this with respect to the gradient taken with respect to x prime. So here gradient is this grad is this, right? The ith component of this gradient is just given by this. But what is, how is this correlated to del del x prime I? That is the ith component of, that is simple enough because x, this is all is inverse linear in x and x prime modulo the minus sign. So when you derive with respect to x prime, it would simply be minus 1 over so grad 1 over r is minus grad prime 1 over r, where this is the space derivative with respect to x prime. Okay. Now putting this in this equation, so from this equation, what I get is this thing equal to d3x prime jx prime, then the minus sign this. There is a scalar. Okay. Now once again I apply this relationship. So I have gradient of something times a vector. Gradient of something here times a vector. Okay. And the gradient is taken with respect to that space over which I am integrating. So once again I use this to get minus 3x prime. Then I have two terms. So I have this here. My A is J and my alpha is 1 over R. Okay. So I can write this as divergence prime J x prime over R minus 1 over R now this is 0 because of the conservation relation which is given. Okay. Because of the conservation relation, this conservation relation. All right. So sorry, I'm having some throat problem. So the second term is 0. The first term is a pure divergence, which you can convert to, this is the integral over volume V prime. So we can convert this to a surface integral. Okay. So you can convert this to a surface integral S over some surface S prime, which encloses the volume V prime. Okay. So then it would be d2x prime, the unit normal to that surface S prime, which encloses the volume V prime, by this. And this surface S prime is arbitrary. So you can make it as large as you like. You can push this surface to infinity. If you push this surface to infinity, you can make this surface as large as you can, whence this integral will vanish. Why? Because J is localized. J is localized within a small volume, and you are integrating over a very, very large space. So to that space, the J is inaccessible. Okay. And hence this integral would vanish. This is a well-known theorem. Wherever you get a total derivative, that total derivative you can always convert to a surface integral, push the surface to infinity, and then because of the localization of the integrand, the ultimate integral, which is basically a sum, is zero. Okay. So what we get here is that this in this integral, this is 0, and the second one is 0 as well. So what we ultimately get is that this whole thing is 0. Hence, we get back to our previous result. So this first integral is 0. This vanishes. Now we are left with the second integral. So we have this minus 1 over c. Then so I have this relation. So ultimately, the thing boils down to this. This is sorry. This is not B. This is curl of B. This is curl of. So we're going to find out the curl of, not B. So this thing. I have two operators. One is this Laplacian, and another one is this integral. So I can write this as, I can interchange them. But this is a function of x prime only. This different derivative is taken with respect to x. So this will come out. So what I'll ultimately get is this. Okay. I'll ultimately get this relation. Now, Laplacian of 1 over r is actually gradient of divergence of 1 over r. And divergence of gradient of 1 over r is minus r over r cube. This is minus divergence of r over r cube. And there is a very important relation. This is well-known identity. This thing is 4 pi times the three-dimensional delta function okay. Those who don't know much about delta function, it is some kind of improper function, which is basically the continuum version or continuum generalization of the Kronecker delta in discrete space. You can simply think of it's an impulse function, that is, it only spikes at a given point. For example, if you take some peaked curve, okay, let's say a Gaussian, and then you squeeze this from both sides. So this will go like this. And as you go on squeezing, it will ultimately come down to be just a point, just a spike at a given point. Okay. It's like you take a bread, okay, and then you press the bread longitudinally, transversally from both sides. Okay, as you go on pushing the bread would get elongated, keeping the area under the curve, the area of the bread intact. So here also, you take a curve, let's say a Gaussian, you push the Gaussian from both sides so that it keeps going elongated along the vertical direction, keeping the area under the curve fixed. So ultimately, in the limit, it will be just a spike. Okay? It will be just a spike like this. So this is what we mean by a delta function. Okay? Delta is basically a spike which, from the physics point of view, this spike is often used to identify or to represent a point mass. Okay? This is used to represent a point mass wherever you have a system of particles with a collection of point masses, then each point mass is being represented by a delta function in the continuum limit. In the strict mathematical sense, there are specific measures, and for this this delta function belongs to what is known as the Dirac measure, which is different from the commonly known. This is a Dirac measure, which is different from the commonly known Lebesgue measure. In mathematics. But I'm not going to those details. Those who are interested can look at the Wikipedia for the Dirac delta function. Okay. For our purpose, it would suffice if we just look into the chapter 2 of Jackson's book, where you'll find details of this Dirac delta function and the properties of this Dirac delta function. Chapter 2 on electrostatics in Jackson's book. Okay. There is a good account of the Dirac delta function, which would suffice. Okay. Otherwise, if you want to do rigorous mathematics, then you look at the mathematics books and so on. Okay. already I'm running out of time. The first lecture is gone. So let me do this thing quickly. Uh, this delta function, this is the three-dimensional delta function. In one dimension, you have a very important property of the delta function, that is, given any function x, this is simply this. In discrete space, remember in discrete space, we recall Fij, Fi delta ij is Fj. This is what the Kronecker delta does in the discrete space. Here in the continuous space, it's the argument which would replace the argument of x in the ultimate result. So this is what the Dirac delta does in a continuous space. We take just the same analogy. Just as one takes the analogy of a difference equation to a differential equation in a continuous space. It's the same thing. When you go to a discrete space, the differential equation becomes a difference equation. An integral becomes a sum. It's just the same. Now, the three-dimensional delta function is delta 3 of this vector x minus a is delta of x1 minus a1, then delta x2 minus a2, delta x3 minus a3, like that. It's just the product of all the delta functions. And it will have the same property. So what we ultimately have is that the Laplacian of 1 over r is minus 4 pi times the three-dimensional Dirac delta function of r, and r is what? R is this. And you put this integral in the integral. So curl of p, therefore, curl of p is 4 pi over c. Then you have, so I'm plugging this back in this expression. So this is 4 pi times the Dirac delta function. So this is d3x prime jx prime x minus x prime. And now I apply this property, use this property. Once I use this property, the ultimate result would be I'm integrating over x prime. So what will happen? Putting the limit x. So ultimately what will come out is 4 pi over c jx. So this is the Ampere's law in differential form in magnetostatics. Apparently, I guess you were told in your undergrad classes or even in some other classes, curl of B is 4 pi by Cj or mu 0 j in SI units. But where from it comes? The derivation is not that simple, okay, as you can see here. So this is how you have to deal with problems which have more than one argument. Okay. So you have to be very careful on which space you are integrating or differentiating over which space, and what are the independent variables involved. All it depends on the independent variables involved. So that is the most crucial thing. Right? So this is problem 2. Problem 3, I think I'll better skip because that is a very long problem. I'll keep this as an exercise. The first 2 parts are just vector analysis in a sort of involved sense, using the Stokes theorem and Green's theorem. I'll urge you to try at home and also try this part, which is the electromagnetic theory. This concerns electromagnetic theory. The first 2 parts just concern the ordinary vector analysis. So you try at home. If time permits, in these lectures, I will show how to solve this. But you first try, and you keep on trying. It depends on how much time I get after the end of what I have planned, all the things in the agenda. The fourth problem is the induced EMF around a moving closed path C is given by this, where E and B are the electric and magnetic field vectors respectively. V is the velocity of the moving path. Recast the empirical relation, which is the Faraday's law, in this form. This is the differential form of Faraday's law. Well, the other day I was doing this Faraday's law, and I skipped the part here. What I did not mention why do I actually require for a moving circuit. This is the Faraday's law for a static circuit. For a moving circuit, the circuit moving with a fixed speed with respect to some frame of reference, say the laboratory frame of reference, then this law, the statement of the law, becomes this. Okay. But for that, you have to have the relationship between the moving frame electric field and the laboratory frame electric field, laboratory frame magnetic field, and the relative velocity. So this relationship has to be maintained to write the Faraday's law in this fashion. That is, the total derivative is replaced by the partial derivative. Okay. But why so? So for that, we have this exercise. We have this exercise. Okay. So let's do it. This is problem 4. Now we have the electromotive force given by integral dl dot plus d over c plus 2. So I'll require to show what is the utility of this type of expression. Why I'm taking this expression for the electric field in the moving frame. And by definition, this is by Faraday's law. This is the time derivative, the total time derivative of the outgoing flux of magnetic field. So this is my Faraday's law. And this is our surface S. The surface S whose boundary is this curve C. And the flux is cutting through the surface S, bounded by the curve C. The electric field is dl dot E prime, where E prime is this thing. So why is E prime written in this fashion? Let's see why. Okay, see the left hand side. Left hand side means this part. So the left hand side is this thing. I can use the Stokes theorem to convert this to a surface integral. Let's convert this to a surface integral. So it will be d2x n dot. Stokes theorem means you have to take the curl of this. Curl of plus v over c cross by Stokes theorem. Unfortunately, the handwriting is pretty bad in this whatever pad I'm using. So this is, so you have two integrals. One is, feel it nice? Okay, thanks. It's pretty bad, I can tell you. Okay, this is n dot curl of v cross b. Okay. So I have two integrals. Now consider this second one. You have to use the relationship curl of v cross b. This is divergence of v using the vector identity. One vector identity is supplied. So this is the vector identity. It is already supplied in the supplied set of vector identities at the end of the worksheet. The divergence of B is 0 by Gauss law of magnetostatics. Divergence of B is 0 because B is held fixed in space. No, not that. B is not held in fixed in space. V is the relative velocity. That is, the circuit is moving with a fixed velocity v with respect to the laboratory frame of reference. So this is your laboratory frame. A circuit is there. The circuit moves with a constant velocity v with respect to this laboratory frame. If you go to any other frame, then this v is not fixed. Okay. So that means, and we are calculating all these things, is derivative, all these derivatives are with respect to the laboratory coordinates. So with respect to the laboratory coordinates, when you take the derivative of v is 0. Similarly here, okay, you'll ultimately take the derivative of v, which is 0. So the term that will only survive is this. So ultimately what you will get is minus v dot del. So putting that in the left hand side, you get minus 1 over c integral, this is surface integral, d2x, then you have c dot del n dot v. So I'm putting this in here. I already have n here, so it will ultimately come out to this. Now look at the right hand side. What was the right hand side? The right hand side was this surface. Right hand side is minus 1 over c d2x. You can write it this way, because in the right hand side you have the time derivative and the integral. There are two operators. You can interchange the operator. N is constant, so it is just the integral over n dot the time derivative of p. Now, as I was telling yesterday, that the time derivative, that is the total time derivative, and the motion has to be taken care of by what is known as the convective derivative. So you have to write this way. Okay. Sorry, I missed another term here. Sorry. There was already a term, one integral, which I missed. Left hand side had this integral. Okay. So let me put this integral here. So I have two terms, the left hand side. The right hand side gives me minus 1 over c is minus 1 over c So when I equate the left hand side with the right hand side, these two pieces will cancel out. So these two pieces are due to the relativistic correction. So what I will ultimately get is dx n dot curl of E plus 1 over C equal to, and this is over surface S. S is arbitrary, so that means this integrand is 0. So hence we have curl of E equal to minus 1 over C. So this is the reason. This is the reason why the moving frame electric field is taken in this fashion. So that when you use the relationship, the total derivative would be replaced by the convective derivative. Then the terms that will pop up will cancel from both sides. The terms due to the relativistic correction will cancel from both sides, and you'll have the same form of the Faraday's law, but the total derivative would be replaced by the partial. Okay. I'm sorry that it took a little longer, but give me just 1 minute break. Okay, I'll bring some water, and we'll resume with the lectures.
Okay, sir.
Yeah, please, sure. So since it is already 1927, I have two very important announcements for all the attendees, and that's the following. We will have 2 more lectures. So today is 7th, and we will have 3 more days with the electromagnetic theory of Dr. Sourav Sur, and we will have 2 days of solid state final capping up with Professor Annapurni, a very famous person in material science all over India. Professor Annapurni is from University of Delhi, the physics department, and she is known in all material science research and nanomaterials research groups in India. And she has kindly agreed to give 2 hours lectures to you all. So she is coming with us in the next 4 days, and Dr. Sourav Sur is there, and 1 lecture by Dr. Savita to end up with your solid state numericals, right? And then on the 11th, we are going to have 1 lecture from the head of the department of IIT Delhi Physics Department, Professor Anurag Sharma, followed by Professor Ajoy Khatak at 6 o'clock on the 11th, right? And now I urgently need feedback from all those who have been attending our lectures by tomorrow morning on the NASI Learning Physics IT. I cannot now wait further. I know there are many more than those who have given me the feedback. You have to give me a feedback, few lines of what you want to say, your suggestions, your feelings, whether you liked it, whether it was advantages, disadvantages, and so on. Okay, whatever you would like to say or share, please do it today night, and I must have it on my mail on Nasi Learning Physics 20 at gmail.com, and that should be done without any failure. So yeah, Dr. Sourav is back. Welcome. Please continue.
Actually, I also have 1 PhD student and 1 intern student attending in the audience. Okay, I guess they can also give feedback. Anyway, let me say
Obviously,
this.
everybody, yeah, sure. Everybody is welcome. So I can recognize the names because every day I almost learn the names which are there in the participant list. So I know every name by now. So a new entry is also recognizable by me, and old entries are also,
Yeah.
and I do need a feedback
One
for the
is
report.
Jaffa Jones, and another one is Subhamay Dev.
Yeah. Everybody is welcome to kindly, and the feedback for EMT lecture for today is already there on the chat box, but please first of all focus on his lecture, and we'll keep the link open, so don't worry.
Okay, let me save this first, and I'll export it to the PDF. And after this lectures are done for tonight, I'll send it to Dr. Bob. Okay, these are saved now. So let's carry on with the. Okay, these are the old set of notes. I can refer to this if you like. Let's open this. I guess the annotations may not be the same. This is a very long file. Let's All right. So we're done up to section 2.4. And we'll start.
Swati, please mute yourself. Dr. Mansi, please mute Swati. Dr. Mansi, please mute Swati B.
Yes, ma'am, I'm doing.
Do it now. Please make me co-host. Thank you. Again, she's not muted. Swati B, please mute yourself. Please make me co-host, Mansi. Dr. Sourav, just 1 minute. Just give me 1 minute.
No issues.
Make me co-host, please. Attendees, if you put on your mic, I will have to remove you. Please be careful. Don't touch your mic position at all.
You are co-host, ma'am.
Okay.
Must be my mistake. She's an old student. I think she didn't see that it has gone unmuted. Yeah, okay.
All right. So as I was saying, telling the other day, that the only option left is to find a new principle of relativity, okay. And also to look for a new set of transformation equations to replace the Galilean transformation equations. So, and so this was the basic motivation for propounding what is known as today known as the special theory of relativity. Why is it called special theory? I'll come later. I'll discuss that also. For the time being, just look at the postulates of special relativity. The first postulate is that this was postulate made by Einstein in 1905 in his celebrated paper. All laws of physics except gravity are independent of uniform translational motion of the system, that is the reference frame in which they operate. This is what is known as the principle of relativity. Okay? This means that all physical laws, except gravity, of course, are invariant under a transmission from one reference frame, sigma, this is the unprimed reference frame, to another reference frame, sigma prime, which is the primed reference frame. I'll call the primed reference frame. And these two, one reference frame is moving with respect to the other with a constant relative speed v. Okay. This is the definition of an inertial frame. All inertial frames will move with respect to each other with relative speeds constant. Okay. If one frame is accelerated with respect to the other, then we'll have non-inertial effects like Coriolis force, centrifugal forces. The corollary to this is the mathematical equations expressing the laws of nature must be covariant, that is, invariant in form under the transformations that leave invariant the infinitesimal separation between two events in space-time. That means all laws of physics will have their same mathematical form. So if we have some form like force equal to mass times acceleration in some frame of reference, in some other frame of reference, this would be f prime equal to m f prime. Okay, so the mathematical form is the same. If uh, if you have this f is if the acceleration is like this, d2x squared is minus some function of time. Okay, let's say this function I take as minus e squared. Okay. In the other frame, it should be then and only then I can call it a law. Okay, so that means the laws of nature must be covariant or invariant in form under the transformations that leave invariant the infinitesimal separation between two events in space-time. Now the concept of space and time, they are not separable. Time is also a coordinate. Okay. So we have 4 coordinates instead of 3. So we have coordinates like x, y, z, x, y, z, and t. But t is measured in seconds. So you have to multiply with some speed parameter. C. This speed parameter is taken to be the speed parameter which comes in the Maxwell's equations. The reason for this is to make the Maxwell's equations invariant under the new set of transformations which we'll find out and which would replace the Galilean transformations. So this is the logic, and such transformations would leave invariant the infinitesimal separation between two events in space-time. So previously what Galilean transformations were doing, Galilean transformations, you remember, they were x to x prime, which is x minus dt, and t to t prime, which is t. These are the Galilean transformations. And they were leaving invariant the separation dx squared. So this was what the Galilean transformations were doing. these new transformations are demanded to keep invariant not dx squared, but the quantity ds squared, which is c squared d squared minus dx. Mark the minus sign. This distinguishes what we should call time and which coordinates we should call space. So although time and space are kept on the same footing, there is a way to distinguish or to pinpoint which one is time and which others are space. Okay. So this is not Euclidean, but this is quasi-Euclidean. And the new transformations from one coordinate system to another coordinate system, these coordinate systems are called coordinate transformations, which we have to find out. Those transformations have to be linear in t and x, as well as those transformations are required to keep invariant this ts squared. Okay. The second postulate is that the speed of propagation c of the electromagnetic signals in empty space is finite and independent of the motion of the source. Okay, so this is the precise statement, and docket it in your mind that this is the precise statement. There are in some books even you'll find some misleading statements that the second postulate is the constancy of the speed of light. That is wrong. Okay, we have not made any allusion to the speed of light. C is just the propagation of the electromagnetic signals, speed of propagation of the electromagnetic signals. And the statement is not of the constancy of the speed, constancy of C. It is that the C should be independent of the motion of the source. So that means C should be unaffected by any effect like the Doppler effect. Okay, so this is what we mean, what was actually proposed. This is the postulate, and the corollary is that for physical entities, that is all material particles or bodies which have a finite mass in inertial frame, there is a finite limiting speed equal to c, as argued via thought experiments. So no material particle can move faster than the speed of light or the speed c. I should not call speed of light because I'll not prove this in this set of lectures. For proof, you have to see Jackson's chapter on the Hertz vectors. Okay. But I'll not do this. There is another renowned book by Born and Wolf where you can see the proof that c is indeed the speed of light. But I'll not do it. Okay. So this thing is that for material particles, that is particles which have a finite mass, non-zero mass, for those particles, their speeds cannot exceed the speed c. That is the upper bound. Okay, this I'll not prove, but because I'll not be touching the chapter 4 of this set of notes. If anyone is interested, the chapter 4 is right here in this set of notes. You can go to the link, download the notes, and the chapter 4 is all about this limit. Okay? But for that, you have to understand the Minkowski space-time diagrams and so on. So those things, because I don't have that much time to go through those things. That is not possible. Only thing I can tell you that if a material particle has a speed c, a speed v, which is greater than c, then weird things, bizarre things would start to happen. The most bizarre thing is that it would violate causality. So the effects will come earlier than the cause. So causality violation will happen. It is actually proved. Let me show you. Uh, if anyone is interested, can go to look at the chapter 4, where chapter 4. I'll not touch the chapter 4. I'll not cover this. This is the whole causality violation argument that is based on thought experiment, but I'll not do this in these lectures. You can, of course, do a self-study based on this lecture. Lectures are at your disposal from now on. Okay. Lecture notes. Okay. The most general set of coordinate transformations which preserve the infinitesimal separation between two space-time events side by side, maintaining the constancy of C. Okay? Or rather, in a more stricter sense, C is independent of the motion of the source. So the independence of C from the source motion are the famous Poincaré transformations. Okay. So in most books, you'll find Lorenz transformations. Lorenz transformations are just a subclass of the Poincaré transformations. Docket this thing as well. In fact, it was Henri Poincaré who is been credited, is often given the credit for the pioneer of this special theory of relativity. Okay. So some people give credit to Poincaré instead of Einstein, this special theory of relativity. But Einstein's theory is most popular, although Poincaré has given this, propounded all these things before Einstein. But propounded in a mathematician's language. And special theory of relativity is a theory of physics. Although relativity is generally taught in almost all the mathematics departments over the institutes all over the world. It's more popular in the mathematics departments. And Henri Poincaré did that in 1903, whereas Einstein's postulates came out in 1905. So Poincaré did it earlier, but this happens with mathematicians mostly because they do the things in a very accurate way, correct way, but without any physical illustration. That is the problem. So until and unless you correlate the things with the physical stuff, the picture doesn't become clear. It is only accessible to very highly intellectual people, not for the standard people. Okay, so that's why Poincaré's thing were not that popular, although it was Poincaré who gave the formulation in a very sophisticated way. But Einstein's things were much more related to the physical arguments, which is rare. One more thing is that the Poincaré transformations, in fact, Poincaré is has the credit of propounding the general theory of relativity also. And in fact, these days, there is one popular version of general relativity, which is known as Poincaré gauge theory of gravity. So all these relativity theories he had formulated as a gauge theory. So that was his contribution. But once again, if you write some article of, I'm not undermining any mathematician, but what happens normally if you write a book on physics, it's much more elegant. Even a paper on physics is much more elegant. Professor Verma can agree with me. But mathematicians' approach, although correct, it's very weird. I mean, what the mathematicians normally do, they don't start with some introduction and after that some thing which explains the physical content and then the mathematical equations. It's not like that. Their thing is, as you all know, if you see mathematics books, it's like theorem, lemma, proof. It's like kind of thing like that. All things, every argument is based on some theorem and then some proof. And all these in these set theory languages. So it's difficult to grasp the physical meaning of them, and that's why Einstein has been credited. But the transformations, the most general transformations are the Poincaré transformations. A surplus. Yes.
Dr. Sourav, you're correct, absolutely correct. I put it this way: the people who love physics always understand the philosophy of nature, the psychology and the philosophy of nature, and that is why each number has its own meaning. Each number along with its unit and where it is in which part of the physics, it conveys a whole story. So because I think physicists and scientists are more artistic than all artists put together. So I think we are all artistic, and that is where we first introduce, build up a story, and then we make a nice thing out of it because we feel nice about it. So
Yeah.
that I think is my feeling towards why we do introduction and tell that this number is important because it gives you this part of physics.
Yeah.
Sure.
Yeah, and the mathematician's approach is quite abstract. It's correct but abstract. So difficult to grasp at a first go.
True.
Okay. So what are these Lorenz transformations? And the general transformations are the Poincaré transformations, and a surplus are the homogeneous Lorenz transformations. Poincaré transformations are sometimes called the inhomogeneous Lorenz transformations. The homogeneous Lorenz transformations preserve the separation even when it is not necessarily infinite. That is, the events are not necessarily close enough. Okay, so Poincaré transformations is what you can have with the most general set of parameters, and that would require to preserve this Ts squared. Okay, so Poincaré transformations preserve Ts squared, this quantity, whereas the Lorenz transformations preserve not only this but also
Okay, I will do.
S squared.
Okay.
Okay, so that is C squared E squared minus X, which is not necessarily
Yes.
squared. Sorry. Um, okay. I have about 6-7 minutes left. I can quickly go through this, and then after that, the worksheet on this will be supplied later on, because I spent much time doing the exercises tonight. So lecture time is curtailed. Anyway, uh, so these are the derivations of this is the derivation of the Lorenz transformation equations. We consider only a very simple Lorenz transformation, which has only one boost parameter, that is the Lorenz transformation for a boost along one axis. So this means that we made a plethora of assumptions. First, we take two frames of reference. The axes of the two frames are parallelly oriented. So x-axis is parallel to x prime axis, y-axis is parallel to y prime axis, and the z-axis is parallel to the z prime axis. Okay. The frame, this frame, the prime frame, moves with constant velocity v relative to the unprimed frame along the positive x-axis with with constant velocity v. The origins of the two frames coincide at the origin of time. So this is another assumption. So basically, what we can do, we can only use the Vx component of. So the V is known as the boost parameter or the velocity. The relative velocity is often called the boost parameter. And this simple Lorenz transformation means that we only have the x component or one component of this V to care about. The other components, there is no motion along the other direction, so there is no transformation along the other components. This is a very simple setup. Now, consider an event whose coordinates are at ct prime, x prime, y prime, z prime in the prime frame and ct, x, y, z in the frame, unprimed frame. As the origin of sigma prime moves relative to the sigma frame sigma with speed v along the positive x direction. So when x prime is 0, x is already shifted by this amount, v times t. Conversely, the prime frame is moving with the unprimed frame is moving with respect to the prime frame with a velocity, with a relative velocity minus v along this direction. Okay. So therefore, when x is 0, then x prime is shifted by an amount minus v. Now the transformation equations between these two systems must be linear. So that for an event in sigma, there is a unique associated event in sigma prime and vice versa. If there is non-linearity, then the associated event is not unique. So if something happens in this frame, there may be more than one things happening realized in this frame. Because if you have, say, a quadratic relationship, then there will be two solutions. So it's multivalent. So one should avoid that. So for an event at one frame, there should be a uniquely associated event in another frame. So if in one frame, the position and time of a certain event is recorded, there should be a unique recording of position and time in the other frame. There should not be any multivaluedness. So therefore, we require the general relationships. And what are the general relationships? You see, this is x prime equal to 0 means x equal to v. Okay, so if I take a relationship like this, where gamma is some constant, dimensionless, then this automatically means that when x is equal to Vt, x prime is 0. So this condition is satisfied. Okay. And similarly, if I take x equal to gamma times x prime plus Vt prime, then again, when x prime is equal to minus Vt prime, minus Vt prime, then x is okay. In differential form, we can just take the derivatives, and therefore, if you work out dx prime dt prime using the these relationships, you land up to this expression. And similarly, dx dt, you land up to this expression. Okay. Now, in the limit, this velocity going to c, both these velocities, there should be, the c is unique by the second postulate. So both this, all the velocities, if one velocity, one frame velocity goes to c, the other frame velocity should also go to c. So in that limit, this equation, the two equations would reduce to this. You can see straight away. You put this thing equal to c, this thing equal to c. Okay, and transpose. Then you have dt prime given by c over gamma times c minus v. Okay, and similarly you have dt prime dt equal to c gamma times c plus v. Now you can just solve them, solve for gamma, and solving this, you get this. Okay. Define some beta, which is v over c, and then gamma is simply 1 minus, just 1 minus e squared over c squared to the power minus half. That comes from this. Okay. Now we have this relationship in, this is one dimensional, of course, and there are, you also have y prime equal to y and z prime equal to z, because there are no frame motions in those directions. So what you ultimately get is this set of relations. These are the Lorenz transformation equations in a simple scenario where there is a frame motion or Lorenz boost along one spatial direction. Okay, x here, and there is no frame motion along y and z. So there is only one boost parameter. In general, there could be three boost parameters, because beta or v by c is in general a vector, and then it will have three components: beta x, beta y, beta z. So there will be three Lorenz boosts or three parameters. But this simple Lorenz transformation just contains one parameter. This is all about one parameter. We'll just stick to this simple setup. In general, there will be three parameters. And also, you have another assumption, that is, the axes are parallelly oriented. If not, then the axes are rotated, and there will be three Euler angles for that. So there will be three rotations and three Lorenz boosts. So 6 parameters in all in the full Lorenz transformation equations. Full set of Lorenz transformation equations. Here we are only talking about a single boost Lorenz transformation. Okay. I'll start from here tomorrow. From this subsection, I'll start. Let's end here, and you have all these notes at your disposal. Unfortunately, I cannot save the annotations here, but you have, I think, the video lectures to access. Okay. So you can see the video lectures.
So you're going to end today's, Dr. Saurav, with this?
Yes, yes.
Okay. So that's perfect. And you have everything. But on this OneNote, can't you save these annotations?
It would be too big a file. Okay, let me try.
I
think
think
it
you can. If you save it immediately, it will be saved.
Yeah. No, actually, I'm using a different annotator, which
Okay.
will not save.
Okay, okay, okay,
Uh,
okay.
But I mean, I have given the web link, so
Yeah,
the
yeah, I know, I know, I know, I know.
be accessed.
Yes, I heard. Yes, I heard. So thank you so much. I'm grateful that listening to you for 5 days will definitely provide a lot of support to all those who are learning or who are yet to learn. And since these videos will be there, one can refer them again and again, and it will be a very good, the inspiration of a teacher who teaches well is communicated, imperceptibly to the students. So I think, and I'm happy that you agreed for this lecture, and it will be there for many generations to come. Thank you so much. So we shall see each other
You are
tomorrow
welcome.
again.
My
Evening.
pleasure.
Yeah. Thank you
Uh,
so much. Our pleasure too. Our pleasure too. So everybody says lots of
there
thank you.
was one question I've just seen. Maybe I can take that question tomorrow. See some question.
Boost in 3 direction in same time. Is it possible? Dinesh Singh asks.
I'm not getting the
8:05 p.m. 8:05 p.m.
boost in the same time. Boost has nothing to do with time. Boost is the relative speed or relative velocity. Time is a coordinate here. So don't mix up with the coordinate and a parameter. Coordinates are variables in the theory. Parameters are the constants which appear. Okay. So boost is a parameter, not a variable.
Any other questions, students? Mansi, please check the YouTube.
Okay, ma'am.
Is there any? So we are going to put the feedback again. Somebody requested for it. Please fill it in the next 5-7 minutes, right?
No, ma'am. No questions on YouTube.
Okay. Okay, fine. Thank you, Dr. Saurav. No further questions for today evening.
Okay, I've stopped the sharing.
Yeah, thank you.
I guess it's fine.
So students, once again, the feedback is there for you all to view on the chat box now. Here it is. Please copy it. Please copy it into your Google browser. And last reminder, I need the feedback from everybody who has been attending these lectures. Please do it today with top priority if you have not done it already. Okay. So, and I know there are many who have still to respond, so please do that. So I was just announcing that on 11th, we'll first have a lecture by Professor Anurag Sharma, who is head of the Physics Department of IIT Delhi, followed by a lecture by Professor Khatak. You will get announcements very soon on your WhatsApp groups, followed by the valedictory, and we shall be ending after that, and the valedictory will not be long, it will be just few minutes. And so I expect all of you, those who have been attending these lectures, to be tuned in on that particular evening. Thank you very much. Okay, okay, Dr. Sur, it was very
Okay.
nice. See
Okay.
each other tomorrow again. Thank you.
Bye.
So students, please copy the feedback link. Yeah, and somebody asked me video or writing. See, I want a feedback. If you give me a video, I'll play it. If you give me something in writing, I will include it in that way. But I have to include it in the report, right? I hope you understand this. When any particular organization does an activity, then in the end, we are supposed to give a feedback. We're supposed to give a report in detail telling whether this such an activity was useful or it was not useful, because only on such feedbacks depends whether such forums will decide to hold such activities for the students. Because if the user is not satisfied, then there is no sense in holding any activity. An activity is successful only if the persons who are receiving it, the persons who are being served are feeling, yes, we did get some help, right? So I hope you understand it. One day you all also are going to grow up and organize events like this, and therefore it is very logical that I require a report and a feedback. If you want to say something, please say it. You're most welcome. Asking for a feedback does not mean that we have you to only praise. If you have a suggestion or something, we are ready to take it. And also on the last day, I will give you option of few things. So some students said that let us be connected on WhatsApp. What if we want to ask about our career? And I said, I will in the end offer to all WhatsApp students, all the students who are on the different WhatsApp groups, to decide whether you want to stay connected or leave. If they leave the group, then then they leave it. If they decide to stay, then we keep the WhatsApp group alive, and you can ask me any question at any time regarding your career possibilities or research possibilities, or any recommendation or any suggestion that you think that we are capable of giving you. Number one. Number two, one of the few students said that we would like to consult you and we would like to have a session on how to go about in a research career, how to go about for doing research and so on. And for that, I answered to that particular student that if you are interested in having such a session in which we speak informally about what are the research possibilities existing in India and abroad, then that can be done only after 11th, not within this series, but after 11, maybe after a gap of 2-3 days. But I should know if people are interested. If you're interested, then I will hold this, and there we will speak about all these issues. If it can help you, it's not a problem. I will arrange it, but it will be after 11th, after 1 or 2 days after that, right? So in case you want that, then you should tell me about it on WhatsApp, or we will on the last day's form or tomorrow's feedback form, we'll put up a question for you. Do you want such a session? You can say yes, no. Another thing is that apart from this series, which was about understanding physics at the graduation and at the post-graduation level, there are many research fields going on in our country, and you as science students should know and should be aware of it. Although a lot of information is already available on internet, but I find that this statement is kind of, weird. Everything is available and still we are seeking knowledge. If everything is available on internet so easily, then why are we all not knowledgeable? That's because internet is like an ocean, and you cannot understand the ocean immediately. You have to first understand the river, the pond, and so on, and then only you can reach the ocean, right? You have to first understand the course of the river, and therefore it is necessary that you understand as you move forward. If by my help you can progress somewhere in your life for your career in physics, I'll be more than happy. So I have no problem in talking to you regarding this aspect. If you would like to have some fields reviewed, for example, it might not be that I am arranging a webinar. It might be that I know that the webinar is arranged and I give you intimation of it, right? If I can intimate to 1,000 people, I can intimate to 500 more. It doesn't make much difference to me, right? So if you are interested, then but the question since for the first day is the following: are you interested? Ask yourself. If you are, then stay in one group and you will get information about various webinars of research level, various agencies, various possibilities of life. And all of you who have patiently attended these webinar series, I can tell you, take my words and mark my words, a person who can have the persistence, the diligence, and the perseverance to sit through a 10-week or an 11-week course persistently is the person who is going to become successful in life. Take my words. Maybe sometime, some few years later, you can search me out again and tell me whether I was wrong. And I'm sure I'm not wrong. I'm very, very sure all of you, those who have persistently attended these lectures, mark my words, you all will be very successful in life, because the success in life comes out of patience, perseverance, and diligence. and diligence. You have to be diligent and never give up. That's the first thing that you have to remember. An electron never gives up. A nucleus never gives up. We do not have to go to bigger levels to get lessons of life. Just look at the smallest particle. They never give up. They go on, and nobody provides them inspiration. The inspiration is nature, and that's also around us. And therefore, we do not need inspirational talks. We should be self-driven, right? And that's what I feel. Well, I've not invested much. The students who are mine, they know that I easily flow into giving some kind of sermons on how to deal life, but it comes automatically to all physicists. So enjoy well, stay well, learn physics, and make a career out of it. Bye for now. Tomorrow we'll have a session on solid state physics by Professor S. Annapurni from University of Delhi and Dr. Sourav to continue with your EMT. Yes? So thank you so much. And you let me know if you would like. Maybe I will arrange few things and I will just let you know. You're most welcome to join. No problem. Thank you. So Mansi, you can now stop the live YouTube recording and also the local recording. So let me know where you